Hi, it's Bruce, and welcome again to my Colorado Rocky Mountain lab. And today I am looking at another Keithley 175 AV auto-ranging multimeter. It would be pretty easy to dismiss this rather lengthy video as another sales video and kind of boring. But that's only if you're not paying attention. There's really a lot going on here. I mean, this is a multimeter. It's got a lot of functions, a lot of ranges. You have to have quite a bit of equipment to test this sort of thing. So just how did I go about doing that? And how did I prove that the ranges are accurate and so on? And what about AC current? I mean, how did I go about providing the AC current needed? Came up with rather an interesting way of doing that, I think, using a function generator and a function generator amplifier, a power amp. Might want to pay attention to that. Then also, at the end, I test the input impedance of the unit, proving that where I should get 11 megohms, I do get 11 megohms, and 10 megohms, I get 10. And then when I go to prove the greater than 1 gigohm input impedance, I come up with a whopping 25 gigohms. And I'm not going to back off. I mean, I think I did it right. So why is it 25? I don't know. But you take a look and see what you think. If you can come up with an answer, I'd really appreciate knowing it. So anyway, enjoy the video. Skim through it if you find parts of it to be a little dry. And focus on the areas where it gets a little more interesting. So thank you for watching the video. These multimeters are nice for a couple of reasons. One of which is they are spot calibration capable. There's a button on there, a switch on the back. You flip over to the cal side, hold a couple of buttons in, it brings up calibration on the unit, and then by using the store clear and recall buttons, you can either go up in readings or you can go down. So you put a voltage on here, calibrating voltage for the range. Like in this case, I'm in a 200 millivolt range, and I would put in 190 millivolts. That's the cal voltage. Then I would hit the release and dB buttons long enough to I see cal written on the screen. I would release it, and I would have some number written on the screen. You know, maybe be 191 point something. Who knows? But I would know that I had 190 millivolts coming in. So if I was high, I would hit this recall button and I would lower it. And when everything's good, then I can hit the buttons again, store it, and flip the switch in the back off, and I've caled that range. Very handy, as long as you've got a couple pieces of equipment to work with. Like you need a steady supply of voltage. In this case, I'm using a Fluke 343, which offers me a very wide range of DC voltages, so I can pretty much calibrate the entire unit DC-wise. AC-wise, I'm using a Fluke 5200A, which is good for anything lower than about 115 volts. And then you need a special add-on amplifier that I don't have, runs more than the original unit. So I'm good up to about 115 volts in cal on AC. And then maybe a couple of nice resistance boxes that are like 0.01%, and you're golden, man. You can cal these things anytime you need to. Beyond that, if you are measuring voltage and you have all of the buttons up, except for the 200 millivolt or 2 volt buttons, like in this case I'll push the 2 volt in, then your input impedance on this is greater than a gigohm. The claim is that if you're on standard voltage where the DC voltage button is in, then the 200, 2, and 20 volt ranges are all 11 megohms. The 200 and 1000 volt ranges are 10 megohms. Then if you lift that button up by like maybe pushing the ohms button until it pops out, and I'm still got the 2 volt button pushed in, then I'm greater than a gigawatt. I wondered how much greater, and what does that mean, greater than? How much greater than? So I went ahead and I measured this thing using some precise resistors in the 100 megohm and 1 gigohm range, and again, the stable supply of voltage. So let's go ahead and take a little walk around this thing. To begin with, we've got a nice stand, still working good. We have a good-looking case. There's a scratch or two on the surface, but nothing really objectionable. Nice-looking unit. Even the back. We'll take a look back in the back here. Power input. This is your calibration slide switch. This is your voltage slide switch. We're set up for 110. I went ahead and took the meter apart. Half of the digits were not showing. They were faded out. So I went ahead and cleaned the zebra strip area, the metallic sides that the zebra strips set on. Clean those up, and we once again have really nice looking dark numbers, so we're good for a good many years. Went ahead and gave the thing a calibration, and we're going to check that in a little bit. We see that we have the condensed operating instructions on the bottom, like most of these old Keithleys did. The feet on the bottom that you wrap your cord around if you care to. Little dented end. One is broken here on the edge. It's supposed to have this little flange on it. Flange is missing, so I guess I'll call that out on that 1 foot. But otherwise, excellent shape. And we're going to go ahead and improve that it functions in excellent shape. Okay, so we've connected up to the fluke. We are feeding 190 millivolts, so we see ourselves flashing from 189.998 to 190. And we see that the 175 is reading 189.99, and it occasionally flashes to 190. There's the 190, saw it. And we'll go to the 2 volt range. We see 0.1899. We saw 190 to begin with. We may see 190 flash on there again. But we're within 0.0001. Here's the 190 volt of being right in line with that HP. Let's go ahead and raise up the voltage. Okay, I've got 1.90000 to a 1, and that is exactly what I'm getting. 1.9000 volts on the 2 volt range. So that cal point's good. Now I'm going to go to the next range, but I've got to push in the volts button, otherwise the readings are no good. We'll go to the 20 volt range. We are getting 1.9 volts, just like we should, and I should be getting 19 within a very small amount. Alright, we have 19 and 4 zeros, with a flashing 1 every now and then. And we see that we've got 19.000 on the 20 volt scale. 19 and 4 zeros, 19 and 3 zeros, so we're good on the 20. Let's go to the 200 volt scale. Alright, we start out at 18.99, so on the low end of the scale we're 0.01 volts out of 20 off, but we want now to raise ourselves to 190 volts. So, okay, I've got 189 and 3 nines to 190 volts, and I'm getting 189 and 2 nines to 190 volts, so looking good. Going to the 1000 volt range, got 190 volts on the low end, and now I've got to decide what I'm going to do voltage wise. I'm going to change my connector. Alright, we put 890 volts on the HP, 890.002 right now, and we get 889.9 to 890 on the Keithley. Yeah, like a flashing last digit there. So looking good. Let's go ahead and check out the AC. Okay, so we've connected to the Fluke 5200A here, and we're feeding it to the Keithley and to the HP. We're currently reading 190 millivolts AC, 500 hertz, and we're getting 190 millivolts AC. Going to the 2 volt scale. Okay, we got 189.7 at the low end, and we bring her up. We have 1.9000, and we've got 1.9004. Let's go ahead and cal that point. I'm going to hold the release and dB buttons in. The word cal comes up. I'm now going to lower that reading. So I got 1.9001 at the moment. 0, there's a 0. I'm going to store that. The cal, the C is off of the screen now, so we're not calling anymore. And we're reading 1.9000 to a 001. So that's looking good. Let's go to the 20 scale. Alright, on the low end we have 1.891 for a 1.9 volt, so we're on the low end about 9 millivolts off of being a perfect reading. Let's check the high end, the cal point. There's 19,000, and I'm getting an 18.998. Let's go ahead and cal that point. Nine. Okay, we're reading 18.999 to 19, and we are reading 19, and I saw an 18.999 a moment ago, so but we're there. So let's go ahead and stop the cal. Okay. Checking the 200 volt scale. 18.94 on the low end for a 19 volt input. Let us go to the limit of this poor thing. 109.000. 109. So we're there. Going to the 1000 volt scale. Alright, we got 109 on the 1000 volt scale, and that's what we're putting in, so we're going to be pretty good there. Can't provide any more AC voltage than that from this setup I have here. Let's take a look at the resistance. Okay, we've got the Keithley connected up to the resistostat. We are on the 200 ohm range. We want to feed in 100 ohms, which is mid-range. This is the cal point according to Keithley for this unit, and we are reading exactly 100 ohms, so we are good. Let us go to the 2K range. We want to go to 1K, and we are reading 1K. Plus or minus 1, I guess, 0.0001. Very good. Let's go to the 20K range. We are reading 1K on the low end. I've got to change this, and we want to go to 10K. And on 10K, we're reading 10.001. I'm going to go ahead and knock that down, so let's cal it. There is 10.000 plus or minus 1 at the end, so 10.000 or 0001. Okay, moving on to the 200K range. We got 10K on the bottom end. It's just a nice check, and we want 100K for the mid-range, and we've got 100.00. Looks good. We're going to take it. Let's go. Okay, we are connected to the new box. We're on the 1 megohm per step. We've got 1 megohm dialed in. We are showing 1.0013 megohms. So we're going to see if we can calibrate that out. Okay, I'm going to hold this recall button in until I hit 0. Okay, and I'm going to give it a moment to come back. Let's raise her up 1. Okay, I'm going to store that. What the heck? Okay, we got 1.0000 megohms. That's good. Beautiful, in fact. Let's go ahead and put in 10. Now on 10, we got to be a little careful because we're going to get very touchy if I move around here. We're going to swing stuff. So I have to wait, let it calm down before I do anything. There we go, 10.000. 0.001. Again, if I move around, I'm going to cause a problem here. But let's just double check the 1. And the 1 is perfect. So there we go. Gone through the resistant range. It's a beautiful unit. It's working beautifully. It's easy to maintain if you've got a couple of pieces of equipment. Provide yourself a nice, calm source of voltage. And if you have another meter that you can trust, the one that's cowled, you can do a reasonably good cow. So you'll keep it in cow forever. All right, we've got to put ourselves into amperage mode. We're using this Keithley 225 current source right at the moment. We're feeding in 100 microamps, and I am reading 100.05 roughly. It's a little bounce around the bottom end there, but and I'm getting 100.05 on the Keithley. All right, let's go ahead and take her up to, okay, we're getting 190 milliamps, 190 microamps, excuse me, 0.1900 milliamps, and we're getting 190 on the 200 milliamp range. Let's go ahead and kick ourselves up in range. We're going to go to the 2 milliamp range, and 2 milliamps, I'd like to read 1.9 milliamps, so let's go ahead and 1.9, and essentially all nines or zeros, whatever. And I am getting 1.8995. I think I'm going to go ahead and cal that. Okay. All right, we're getting a 1.9 triple zero and 1.9 essentially triple zero on both. So we're looking good at a 1.9 milliamps. Let's go ahead and kick ourselves up 20 milliamps. And okay, and at the 20 milliamp position, we're getting 19.00, well, 19, consider it all zeros. We're getting 19.000 on the Keithley. So that's at the 20 milliamp setting. At the 200 milliamp setting, we're reading 1900 on the low end. And I'm just about at my limit here, but we'll see what we can do. Okay, so we got 100.00 milliamps on the Keithley and 103 zeros on the HP. So we're good. And if we went to the 2 amp scale, we're reading 99.9 milliamps right now coming in. That's at the limit of this 225, so in order to provide a little higher current source, I'm going to need a different power supply and setup, so we'll see what we can do. All right, we're getting 1.002 amps from this power supply, and we're reading 1.0019, or, well, actually we're changing constantly here, 1616, so we're right on the money at 1 amp. So there we go. Current scales look good too. Okay, so now we're measuring the AC current. And there is no calibration for AC current specifically. You calibrate the DC current, so you're calibrating all of the current that you receive through the shunts and so on, and then you feed the signal into the AC voltage converter, and you convert the signal to DC, and then you measure it. So it's a combination of the DC current calibration and the AC voltage calibration that makes this thing work. So we're going to proceed from there. I've got a little jerry rig here that we'll use to provide verification that it's working. There is a verification table for the current. I don't have an AC current source that's specifically made as a calibrator, but I have worked up a temporary solution to generate current, AC current in specific packets. So what I've got is a DDS function generator, a power function amplifier, a precision 10 ohm resistor, 50 watt. Turn the fan on just to keep it cool. And what we're doing, we are feeding the signal from the DDS source into the power amplifier. Coming out of the power amplifier, then we're taking the negative lead into the negative side of the current meter. Coming out of the current meter, we're running into the, well, in this case it's the positive terminal of the load resistor. Then we're coming out of the resistor and we're running back into the other side of the function generator. So we're measuring current coming out of the function generator as it passes through the precision resistor. And we're measuring that AC voltage on that precision resistor using the HP back here. And knowing the resistance, and we measured it ahead of time, knowing the voltage on it, we can determine the current going through it and get a pretty good idea of what should be displayed on the meter. So, okay, so we've dialed 1.948 millivolts across the resistor. We're showing a Keithley reading of 189.9596 microamps. Essentially 190, but let's go ahead and pop the number in up here. We have 0.001947, and we're showing 195 microamps would be expected out. 195 microamps for that 1.947 volt in. So we're showing about 5 microamps of difference total. Let's go ahead and take a look at the 2 milliamp scale, and let's 1.9009008, 1.90, excuse me, that would be 19.010. 19.010 millivolts. 19.010, and that's saying I should expect to see 1.899, 1.9 would be milliamps, so very, very close. 1.899 to, and instead we go 1.9008, so 0.8 microamps difference, something like that. All right, let's go ahead and do the next level. Okay, we're on the 20 milliamp scale, and all right, we've got 18.977 milliamps, roughly 19. We've got 189.63 milliamps of AC, not milliamps, 189.63 millivolts. So 0.18963. We should see 18.946, and we've got 18.977. So I don't know, it's roughly 0.03 milliamps, or about 30 microamps of difference. Let's take a look at the 200 milliamp scale. Okay, and we want to take ourselves up to 190, Maybe I can fidget just a little there. 190.22. 23, okay. So I've got 1.8 and 3/9 volts. 1.8, 1, 2, 3. I should be getting 189.8 milliamps, and I'm getting 190. So 0.2 milliamps difference. Not sure what to make of that, but it's certainly right there in the realm. And finally, we're on the 2000. That'd be the 2 amp scale. I could maybe try and get this thing up to an amp. There's 1,000.1 milliamps showing on the Keithley. I got 9.990H. 9.990H would give me 998.2, and I'm showing 1,000, so we're two milliamps difference out of 1,000. So very close. I'm going to go ahead and relieve this thing. Keep it cool. So anyway, we've demonstrated that we're getting what has to be very close readings in AC current. I wish I had a precision source that we could use, but it's still a good check. So bear with me and we'll keep going. Well, the impedance of this Keithley 175 is supposed to be 10 megs for the 200 volt and 1000 volt range, and then it's supposed to be 11 megs on the 200 millivolt, 2 volt, and 20 volt range whenever the volt button is pushed in. But if the volt button is left out, then on the 200 millivolt and 2 volt range, your impedance is supposed to be greater than 1 gigohm. Key thing though is it says greater than. It doesn't tell us how much more, but the assumption would be that it's somewhere around there. So just how do we go about maybe trying to measure this? Okay, so basically I have the Keithley here. It's represented by this little analog voltmeter, which it isn't, I understand, but that's an easy way to draw it. Here's my voltage source. I'm going to have a series resistor in line with that voltmeter, and I want it to be substantial. So I'd like to pick a resistance that's up around whatever the resistance of that meter is expected to be. So I'm going to go for the 10 meg to begin with, because 10 is close to, well, it is 10, is equal to 10 on the 20 or 200 and 1000 volt range. And it's very close to 11 meg, which is the other ranges, so I should be able to get a substantial voltage drop across that resistor, which is what I'm looking for. And by doing that, I can calculate what the current going through both it and the Keithley would be. Once I know what the current through the Keithley is, and I also know that the voltage across the Keithley is going to be equal to the source voltage minus the voltage I measure across the series resistance, then I can take voltage divided by the current that I calculated, and I come up with the resistance of the meter. So we're going to give that a go. That's the whole expected thing. Here's my, I expect my impedance to be 10 meg on the 200 and 1000 volt range. I expect it to be 11 meg on the 200 millivolt, 2 volt, and 20 volt range, and greater than 1 gig on the 200 millivolt and 2 volt range. And then, so the steps for the determination, I said hook up the circuit, measure the source precisely. So we're going to go for 1.9 volts on the 2 volt range. That's the calibration voltage point and should be accurate. We're going to measure the voltage across R1 very precisely. We're going to pick R1 to be very precise. I happen to have a couple of resistors that I've measured very precisely. So having a precise voltage and a precise resistor, I can come up with a precise current. That's the idea. And then I can calculate the voltage across the meter, the Keithley, as being the source voltage minus the drop on the resistor here. And I can calculate the current through that Keithley. The current is the same as the current that's going through this series resistor because it's all a series circuit. Well, the current going through here is going to be the voltage across it divided by the resistance. That gives you the current. So once I know the current here and I know the voltage here, then I can determine the resistance of the meter itself. It's all Ohm's law. It's pretty basic. And we're going to see what happens. So bear with me. All right, so we've wired the thing up just like I said. I have a 10.192 megohm resistor right here. I'm right now measuring the voltage coming in from that Fluke 343A up there, and I've got it set for 1.9 volts. And I am getting very close to 1.9 volts now. So 1.8, 999, and I saw it flash a minute ago to 9. We can adjust that. Okay, and we'll check it again before we take the measurement. All right, so I've got 1.9 volts coming in with the circuit wired up. And I can get this back here. I'm going to measure the drop across that 10.192 megohm resistor. Okay, so on our first set of measurements here, we show 0.9904 volts on the Keithley, which we'll double check that in a minute, but the Hewlett-Packard is set up right now so that it's measuring in its highest impedance state. So we're getting greater than 10 gigohms here. So we're quite large compared to the expected 11 meg. Okay, we got 1.90000 volts coming across the circuit. All right, I've got 0.909. Looks like 0.9096, and that would match with the 0.9094 that I had on the meter there. If I move around, I change the readings a little bit, but 0.9096 volts across the resistor. The resistor is 10,192,000. That gives me 8.9 times 10 to the minus 8 amps going through the circuit. The voltage across the voltmeter is 0.9004, which it read anyway. And that would give me an 11.097 megohm input impedance. And I expected 11. So, yeah, we're right there. It's 11 meg. That's in the 2 volt scale. And it would be the same in each of the scales. In the 20 volt scale, I got 0.909, I would say 7. And I still get 11 megohms in the 20 volt scale. Let's go to the 200 though, because it should drop according to the specs. Okay, so I'm in the 200 volt scale. I am showing 0.954 I would call it a 9, 0.9549. 0.9549. Oops, 9. And that winds up giving me a 10 megohm impedance, which is exactly what I was expecting. So Let's go ahead and do it for the 1,000-volt scale. And .9592 looks like 9592, and I got 9,996,490, so 10 megohms. It's exactly what we expected to see. So we've done well, confirming the expected results on all of the ranges this way. But now we want to lift that volt button, and that should set us up for greater than a gig, and we want to take a measurement there and see what happens. Okay, so we're set up now to measure the impedance of this Keithley with the volt button pushed out, so that we are supposed to be greater than 1 gig in the 2-volt scale. The series resistor I'm using is 10 times greater than the one I had earlier, so I'm 99.830 megohms. So about 100 megohms, but we're going to use that exact measurement. I have 1.9 and 4 zeros for volt that goes across the entire meter network. And if I don't move around too much, we'll allow this thing to calm down. Alright, so using this setup, I'm getting about 7.9 millivolts. So at 7.9 millivolts across that resistance of 99,830,000, I've got about 24 gigohms of impedance. And I'm expecting greater than a gig, but I wasn't expecting 24 times that amount. So, I don't know. That seems odd to me. We're going to try a different series resistor and see what happens. Okay, so what I've done is I've just placed a 0.01% 1 gig ohm resistor in the circuit, and I'm allowing the voltage to stabilize now across the resistance. I want to see what I'm going to come up with. So I'm going to just sort of sit here calmly and let that sort of stabilize. 72 and 73 right now. So let's see where that puts me. We're going to say 72 millivolts. So 72. And we're using a 1 gig ohm resistor. And if that's true, then I've got 25.3 gig ohms of impedance. Well, we just measured 24 a moment ago, 25 using a larger resistor and getting larger voltage values that are more readable, but that's very interesting. I mean, we're 25 times essentially what we expected to get. I don't know what to say about that, but it seems to be true. Well, so there we have it. We've taken you through DC volts, ohms, AC volts, DC amperage, AC amperage, and then we even went into measuring the impedance on this thing. And we showed you how it works. So I hope it hasn't been too boring or long, and that it might find it interesting. It's a nice little meter. It's performing well. I think it'll make somebody a nice addition to their bench. Thank you for listening, and we'll see you again next time. Bye.